here you have information. Okay, I see that otherwise it's negative. Sorry.
So you're saying that knowing in additional. So in all the in both cases we predict y something.
Yeah.
And in all cases you know all the previous x's and y's according to this picture. All x up to x I minus 1 they are known to. But the question is whether you know x2 or you don't know it. And if knowing x2 helps, this means that there could be an information flow directly from the random variable x2, not only from the previous variable. So we can believe that y2 is happening somehow is influenced by x2.
Yeah.
So we want to know that whether there is some information leak between x's and y's.
Yeah.
So imagine, I don't know, x1 is the bank policy and the regulations policy, and y2 are actions of some dealer, and we want to know whether it gets in line inside the information or it doesn't. So if it doesn't, then knowing the current today's decision of the regulation agency should not influence today's dealings. And but of course knowing the yesterday's information can influence today's dealing. It's legal. What is not legal is just that today's action helps to provide. Yeah. Okay. So is the motivation clear now? More or less. So theoretically, we can try to so this kind of application by.
Why do we interested in online complexity of a pair? Right now, it isn't clear why it is interesting.
Complexity
of a pair.
Oh, why the initial question?
Yeah.
No, it's up to now it's not related with this motivation.
It is motivation for online complexity.
This is motivation for online complexity,
okay.
And then of course we want to understand that technically how it works and what it means, and then we are looking at.
Yeah, now you can do this for different screens. You can make such equations, and then you want to see whether some questions will give the same answer or not. I'm very sorry, but I cannot explain all the details now. I'm not so talented that I know everything by head. But the point is, you've got different screens with question marks, and you can ask whether some screens are equivalent. And this is exactly equivalent to additivity of Kolmogorov complex, online Kolmogorov complex.
So your claim, which is that you can write two pictures, two informal questions, and then you can ask whether it is the same. Is it possible that what information leaks exist here and doesn't exist there, or they are equivalent? These questions are equivalent. And if the information online complexity were additive, then these legal questions will be equivalent.
Yeah.
And since it's not additive, they are not equivalent.
Exactly.
Okay, but you need to prepare more to explain what are these two schemes.
Yeah, I cannot do it directly.
Okay, but so we postpone this.
Yeah, but I will go one step further. You can also make a third screen, and ask whether the three are equivalent. And this is asking whether there is additivity of online complexity and there is symmetry of that symbol. So the question is, do you have this one?
So there is another formal question.
Oh, that's easy. You can ask whether. Oh no, sorry.
No. So there is some formal question about the equivalence of these two quantities, and it corresponds to some informal statement which says that information leak in some way is equivalent to information leak in other way.
Yeah.
But can you say which kind of information leaks are equivalent, are corresponding to the left and the right hand side?
But that's with hidden states, so I must look carefully and explain it to you, because this is without hidden states, this scheme, but this equivalence is some scheme with hidden states, and it's a little bit, you need to be very careful which arrows you draw and so on.
Okay, but okay, then let's understand simple thing. So you claim that additivity is not true. For the pair, and this equation is also not true, or it's true.
Exactly, it's not true. That's
so it's a formal thing, which we can try to.
Yeah.
And this is also delicate example, or some kind of simple thing which we can.
Yeah, I cannot explain that. I just wanted to give a short motivation.
Okay. Can you write just the formula in terms of arrows, just for this why? So what is given?
No, but Shasha, I think it's better if I try. I will make mistakes, and then you will get bored.
No, it's very instructive to see your mistakes, because then we don't do these mistakes ourselves.
No. Do you also agree, Fireskagen? I actually questioning, should I give now the proof of violation of online additivity, or should I go into the motivation?
I'm in favor of the proof.
Okay.
Actually.
Yeah. I think it's better, because that's easier to explain than this, because I know quite certainly that I will make many mistakes, and it will cost a lot of time. If I can prepare it, the talk, then I can give it much shortly.
Anyway, it seems that Bruno is not very prepared to explain these motivations, and we can just postpone.
I just wanted to
there is another idea when looking at an unprepared explanation. You see usually much more than when looking at a prepared one.
No,
but
not in this particular case.
Okay.
But otherwise we can do it with our two on another moment.
Okay.
I just wanted to say that there are motivations in terms of such schemes, which I don't remember now. That you want to prove if you have additivity of Kolmogorov complexity, then such equations follow directly. But since we don't have additivity of Kolmogorov complexity, so I will write this out. Yx minus minus
okay, but either we discuss it or we don't discuss it. If we don't discuss it, just forget about this equation.
Okay, yeah.
And because
no. Yeah, but then you can switch it, and then you cut out.
Okay, but
I will show it the way now. Okay.
So now we have a counterexample for the additivity, for complexity.
Yeah, but the reason why I wanted to explain this is because Mushnik wrote a paper and Chen wrote it down and published it, which has some parameter, and if you keep that parameter fixed, you also have a proof for the violation of online complexity. This is the parameter h. He lets it goes to 0, so he constructs random strings for which there is a violation, because h goes.
Either we discuss Mushnik paper seriously, or we just say formally that you say that you can get another proof of another example of the non-additivity using the technique developed by Mushnik, but with some different parameters.
Exactly.
So, okay.
Yeah, but you should know it, because you should make a decision whether we go to the proof or not. Then at least if we start, we should know for certain that we want to go to the proof, that we are sufficiently motivated.
Your proof.
Yeah.
Okay,
exactly.
let's go to your proof without
distraction. May I?
Sure.
Yeah. And okay, you,
Yeah.
when you clean, I will ask Sash one question. So when we speak about complexity of the pair, we mean that the bits are interleaved. X1,
Y1, X2, Y2.
And when predicting Y1 we know X1, when we predict X2 we know Y1 and so on.
No, when we predict X2 we know we know all the things which are
both X's and Y's with smaller indices, right?
Yeah.
Okay.
So in both terms we have online complexity. We predict next term knowing the all previous things.
But is it true that one of these online complexities is just arrow and the second is arrow plus in this notation?
Probably. I don't really. This arrow means something which is not very clear for me. But I guess that it should be like this. But these things will not appear in the same equation. They will appear x with addition. So just write the equation. Yeah. So you
Now, there is some observation which was given by X, which says that for any string V,
and K is a prefix complexity.
yeah, prefix-free complexity.
So here it's prefix-free complexity, but when we look for our question, it's not we don't think about prefixes because we are up to a linear terms, and so we can take any complexity, but this is prefix complexity.
Okay, do you prefer V to be natural numbers or binary finite strings?
This is one thing.
Because it does not matter for the proof, so it's just for notation. So
why do you ask? Is it important?
Okay, just write the.
Okay.
Let
binary strings. So
Okay.
I take it's then some proof of gap size within some log V. So this is a result of checks. He shows that complexity of complexity can be high.
So just let's explain why it's important. What it means in terms of why it's not it's symmetry violation. How to say? Can you explain for
why it's important for this proof?
No, how it's related to symmetry violation.
You choose now. I do not take the online setting, but just
normal prefix complexity.
Yeah. Then we have we can choose y equals kx and x equals x. Then we have that ky given x minus kx given y. This one equals kx. This one equals kx minus kx. I should do another thing.
Let me explain this. So there is a formula that if the complexity of a pair is equal to complexity of W, because if we have a program which produces a prefix program which produces W, then automatically it produces itself the length also. So this is But if we want to have complexity of, if there will be additivity, one can write something of the second terms when first is known. So one can think that this will be small. If the additivity will be very exact, it will be this term should be small, because this is equal to this, so this should not appear. But
this is not true.
But this is not true. For some strings, the complexity is close to L of L. The complexity of W is close to its length. So the complexity. This is close to logarithm of the length. So this is almost maximal. So, and who proved this Gach, or who found this can happen?
Vitali said that it was Gach.
Yeah.
But maybe somebody else did it independently because of the Russian-American situation. Now you can do symmetry of information, because you can write x given y as plus ky.
What are you explaining now?
I'm linking this result to the symmetry of normal mutual information. So I'm saying that
But it is symmetric that you have written.
This is symmetric indeed. Sorry.
But wait, I think we understand how this this inequality relates to the non-symmetry.
So I have some even understanding from a previous explanation in Marseille. We know that there are some small difference, still small difference in the equations for pairs, for prefix complexity. But now, when we have the online thing, this difference, which Bruno said, can accumulate for every online step. So if it accumulates, we get some linear.
But the problem is that the difference matters only from long strings, and in online settings our xy's are bits. So how we can have any difference?
Of course, formally we cannot use it because everything is defined up to a constant, and for one bit this constant.
So should we define our sequence into blocks and use the difference for blocks? But how do we obtain anything if the length of the block, the number of the blocks is not constant? I mean, the number of the blocks should be linear, right? Then that means that the length of the block should be constant. But do you mean that we choose a very large constant so that to obtain?
We choose a small constant, so we choose a small difference, but we use a lot of blocks, a linear amount of blocks. But the problem then, there is some problem because we should add online complexities in another way, but we're just showing that you cannot add online complexities. So then we are in a problem, but we can get out of the problem. And this is the whole difficulty of the proof. So I will explain once more to be certain that you understand it.
So you want to explain the proof of this result?
Yeah. So now we go back. We have this formula, but we can relativize it.
No. Sorry, you explain the proof of Gach's result now, or you want to use this claim?
No, I will not prove Gach's result.
But you will use Gach's result.
Yeah, exactly.
So you will use this result without proof?
No. As I understood, first of all, we need a relativized version of this result. So just write down.
So relativized version. Oh, you try to read this proof.
No.
in the paper?
No, I didn't.
You gave up earlier.
Yes.
Yeah, okay.
I gave up when I was finished with chapter 3.
Yeah, I'm very sorry for my writing, and the problem is I do the best I can.
Okay, don't, no problem. Just write the right version.
Write the revised version.
There.
Yeah, I see.
Is at least exactly the same. So if you look to the proof, then you can assume any oracle on the device and it's still working. So then you come up with such an equation. So here is the same. So the proof still works if you put an oracle.
Just write
on
the
it.
second part.
But it is the same.
But for example, there will be length of what?
W.
Only W.
Okay. For W given by given Z.
Log length of W minus log length of W. And now what are the quantifiers?
So the constant is independent of V and V.
For every V there is W.
No, for every length
For
of...
every V.
Just say it exactly. You need for every... Say the exact statement. For every V.
Yeah.
For every V and N.
Every V or every N.
There is W.
There is W element of 2N. Such that this holds.
W of length N. Yeah?
Yeah.
So the complexity of when W and V is known is greater, so it's just greater than log N minus log N, yeah?
And the constant is this inequality is universal, so where is this such a constant then?
Yeah, so this is the Gotch result, and do you remember the proof of it?
It's very tricky. The proof in Vitani's book, and which is the same as in the Czech's online notes, is a little bit tricky.
Whose online notes?
Pages. Czech's has online notes, but
Gotch, you mean?
Gotch, yeah.
Yeah.
You say Czech. Sometimes you say Czech.
Oh, sorry.
No,
it is Czech's. What is it?
No, the name of Peter, the last name of Peter Gotch is Gotch.
Gotch.
Sometimes we say Czech, and we don't know whether it's the other just a kind of alias for Gotch or some other thing. So
Gotch.
Peter Gotch.
Peter Gotch. Okay.
And he's not Czech, he's Hungarian.
Yeah.
So,
okay, Gotch.
yeah, but it would be. I think we should find out this proof, and it's not good that we don't understand it.
Yeah.
So we should.
But you can derive it from the original one just by assuming an oracle with V on the machine.
Yeah, but the problem is that we don't know the original one. We should know. I think somebody explained it to us at some point, but okay. So it's probably a good homework for Ilya. So you can try to invent the proof. Maybe it will be simpler.
No, you cannot reinvent it unless I don't know how smart you are.
Why such an insulting theory?
Is it true also for plane complexity?
It's explained in Vitani that's also true, the proof for plane complexity.
No, it's because for difference between plane complexity and
yeah, but the proof works for both, so it works.
Just the statement is invariant. The difference between plane complexity and prefix complexity is about the size of the logarithm of the complexities.
So it's log.
It's log. I think log terms. So
no, it's a one. There's not it's you can do it with one log.
Okay, with one, but it's important that it's one for you.
No. I just want to hint that the result is not so trivial, and unless you're very smart, I don't think you will.
He is.
Yeah. So
then that's your homework.
No. I think that knowing that this game interpretation, we should understand what the game is, and it should not be very difficult, and definitely, I can explain this. Okay, but. let's keep it now, and we will not try to reconstruct it now, and let's try to use it in your argument.
Yeah. Can I remove this?
Probably. But the more you remove, the better, so we don't need to remember it.
So now we're gonna make. First, I will give. I will try to prove it by saying we got the relativized version. So we could make a sequence we call x test. We call y x y. And so on. Then this sequence, we can expect that this will violate this additivity.
And the third term in the second column, it is
K of something wrong there. So there is not K of Y1, W1.
K of W2 condition of W1.
No, something is wrong in the form.
So, you've got Y2, K1, Y1. So,
and W1, W2, W3, it is individual bits, or it is
no
strings?
There are some blocks, I guess.
Of strings.
There are some strings, but they probably will of bounded length. But the bound is rather big compared to the constant in the gauge difference, I guess.
Yeah, we will take a very long sequence. We can extend it arbitrarily long. So, and then we use.
And would you please write in the left part? So the scheme we try to violate. The first one, complexity, is the complexity of predicting y1 given x1 and so on, right?
No, I think the order is like this. We start with this, then we have this.
Just write the arrows, Sasha.
This.
Write the arrows
Yeah,
for the memory. This is the first complexity, right?
Yeah.
Okay.
And the second complexity
like that.
is like
Yeah.
this.
Okay, good.
So the sequence goes in this direction, and we just split into left part and right part. This is what we are doing. This is my understanding.
So, and then the complexity of y given x.
For these three inequalities, if we agree that we will do all three inequalities, then we've all understood the first inequality.
Yeah.
But we don't understand yet the second one and the third one.
Yeah.
So you prefer to start with the second
or
or...
difficult thing of, yeah.
Okay, so you prefer to start with the second one or the third one? Let's make a decision. Let you make a
I
decision.
will, actually, I build up a theory and they follow both quite simultaneously. So
you want to prove some lemma which will be useful for the second one and the third one?
Yeah, the lemma will imply the second and the third one.
Yeah.
However, we can only show these results if we have additional information. So we will need to introduce more strings that provide additional information, but those small strings have a very small complexity. So they will interfere with these results, but they will interfere only within a very small error. And then the result will follow.
So we will not prove them directly, but we will do some modification.
Yeah.
Okay, but then the last question before we switch to your lemma is, you wrote something here on the left. But there are some formulas here.
Yeah.
These are explanation of what?
What's standing here, it's about the same, just otherwise. So it's actually a motivation for these three inequalities.
Okay, so we don't need to understand them.
No.
Okay, then we can
if we
arrange
understand
them.
this, then
I think we
can
understand
forget about
this. Yeah.
That's very good.
Okay.
There.
Okay. So now we switch to some lemmas.
Okay. So for the lemma we will need the lemma for this in the two cases. So I will use an abstract notation.
So you want to formulate some general lemma. Okay,
Yeah.
what is this lemma?
So, but first I will say that I will call these things, I will call this a task. And the task consists of a question 1, and then you compute an answer 1, and then question 2, answer 2.
Okay.
And this whole thing you call a task.
Yeah, and task has some complexity.
Exactly. So task you can give k thing, but in a task you can also assume some number, which we will call n, and we know n in advance. So
Just a condition.
condition, yes.
But you can just use vertical line to show this
Yeah.
condition.
So
Okay.
so when we say k thing, we assume that we know the number n. Then we can also consider the subtask, which is just from answer I minus 1 question I. That means the first I minus 1 answers, the first human we compute answer, the ith answer. That's some notation.
Qi, Q super I is the sequence of all
Yeah,
the
the-
previous questions. Okay, good.
I
Okay.
equals, or I equals Q1.
I see. You don't need to write down it. Okay. So you use superscripts to refer to the sequences. Good.
Yeah. Then the lemma says, I will write it here. Lemma kt minus and some So it says that the complexity of the task is bigger than the minimum of n, and the sum of the complexity of all the subtasks if we have some additional information. That is what the lemma will say. Now I still need to define the additional information, how that is defined. So you understand. So for any task,
But wait, what's the complexity of the task? Do you mean that when we solve the task n is known or not?
Yeah. So n is given always.
The left side is conditioned on n actually, yeah?
Yeah.
And as for the right side, it is conditioned on n too.
But that's
Yeah.
strange that in my view n should be relevant if it is given in condition, but still you have it in the right hand side. How come?
Okay,
Can you repeat?
I didn't understand. Can you explain me what is the right hand side? There are some formula, k of something. What
Okay.
it is?
No, I don't know what it is.
So, but informally, this k, what is k of ti
Yeah. So
at the shortest problem, which does what?
yeah. Actually, it's indeed, it's probably a too complicated notation. KPI equals K answer question I, and then you also got the N.
So it's not online complexity, it's just prefix conditional.
It's just one task of online complexity.
Okay, but we don't have K of Ti in our lemma, right? We have something different. K of Ti given
some additional information. So
L.
And n is the length of a sequence, or it's just any number? This big N is just the number of questions and answers.
Any number.
Arbitrary number.
Yeah.
And the sequence has some other length.
Yeah.
So what is L?
So L is any number. But you need the definition. I will give now because the definition is a little bit complicated. L is actually the number of solutions for the task until I minus 1. So it's the number of programs of length n that solve the task until level I minus 1.
Of which length n?
Yeah, big N. But I will write down the formal definition now.
But wait. Isn't it formal what you have said?
No.
I have not yet defined LT1. LT, I will define it now. I will write down the definition.
But wait.
Oh, sorry.
Wait. You have just said what is L.
Yeah.
Is the number of the programs which solve the task, right? Isn't it?
Yeah, exactly.
Why do you need to write it?
Okay, if it's sufficiently formal, then I can continue.
I think so.
Yeah, but then explain, if you understand something, just explain it.
Okay, we consider Ti. Ti is the task of producing I answer.
Knowing all the previous things.
Yeah.
All the previous things. And the answer is, some string.
Yeah.
It's a parameter of the whole definition.
Yeah.
So there can be many programs of length n which solve that task.
Exactly.
Which length is capital N.
N, as I understood, it just indicates the length of the preferred program to solve certain task.
Yeah.
Okay, so there could be many such programs.
Which solve all the interactive things up
Not
to
all.
level N.
As I understand, we have a sum over I, and n doesn't depend on I. So for each I, we are interested in programs of length n to solve that task, T sub I.
Yeah.
And L indicates now the number of that L. Does L depend on I or not? L. Should it be Li or not? L. Does it depend on I?
LTI?
Ti.
Yeah.
It depends on I.
So what is L?
L is the number of programs of length n to solve the task Ti.
Yeah, but there is a subtlety. Ti with I above equals. That's why I wanted to write down the full definition.
Wait, just say it in words. What is T super I?
It is the amount of programs that solve the task here until I.
Until I. Okay. So we have two different tasks. T sub I, which is written here.
Yeah.
And T super I, which is below. And T super I is the problem of solving I tasks. All the TIs actually, up to I, right?
Yeah, so it's online complexity up to some level.
Up to I level, right? And we are interested in programs of length n to solve T super I. So all the tasks up to level I, right? And Li refers to the number of such programs.
Exactly.
Of length n.
Of length L.
But it's a very complicated number, really. The number of
Yeah.
programs probably is very delicate thing.
Yeah.
Because
Exactly.
Oh.
The logarithm of the number. So it's logarithm of that number.
Okay.
I will write down to be completely sure the definition. So I say.
No, but
I think it's better because we should
You
agree
should-
on that because it comes up again and again and again. So it's important. So we define the solution set of a task. Tn. But your explanation is right, but to be sure, to confirm, I will write now
Okay.
down the solution. So the programs of length n.
But do we want them to be self-delimited, by the way, or not?
Yes, for a prefix-free Turing machine.
So if they are shorter programs, we don't count them. Still. We want them to be prefix-free,
Yeah,
exactly of length n.
yeah, exactly.
So shorter programs which do not read all n bits are not counted in this formula.
Exactly.
Strange. Okay.
But it does not matter actually. But I will stick to my definition. Otherwise, it can be dangerous for mistakes.
No, there is no danger of it.
Yes, there is.
We will get into it anyway.
Of minus 1 QB n down to 1.
Yes, you write a formal definition.
Yeah, of the set
Yeah.
containing all solutions of the task
Yeah.
T.
In the hope that it will be formal and exact. But then we know that we see that you have small n in the right hand side and
Yeah.
big N on the left hand side. So what does
So
it mean?
T is a task of length n. Of length n. So these are all the solutions for the full task.
But I don't understand. For example, this program P. This is a self-delimited program. So
Yeah.
Turing machine reads something of this, and you claim that it stops reading n large n
Yeah.
bits. And so, but here you have the conditions ai minus 1 and qi. Yeah.
Yeah.
And you say that it still stops after reading n bits for every I.
Yeah.
Yeah. So if n is given, it doesn't matter. It knows the if n is given, why you say that p is self-delimited? I don't understand. So if n is the condition, so the program can know how many bits it should read. So why we require it to be self-delimited?
Okay, it does not matter. That's true. It does not matter because we know n, so the program knows.
Okay, yeah.
Could you possibly explain what does this mess mean?
Which one?
This strange set.
This strange.
What is big phi, for example?
This is a Turing machine.
We say that P is a program which converts, reads AI minus 1 and QI, and reads
So phi is a universal Turing machine.
Yeah. Phi is a
universal Turing machine.
Okay.
Then down arrow equals means that the machine stops.
Stops and outputs AI.
Yeah,
AI.
exactly.
So we look how many programs of length n can answer all the online questions up to a certain point. So for example, I guess that when small n increases, then this quantity decreases.
Why do we require p? Why do we add n in condition?
Big N in condition because we need it for the proof of the lemma.
No, actually, we want the program p.
So why do program should its own length?
Because we don't want to worry whether are self-delimiting or not. If the program knows gets some how many length it should, how many bits it should contain, then it knows when to stop it.
So isn't it strange that the program is given as an input its own length?
No, probably it's kind of it's a way of to get rid of self-delimiting condition.
Why do we need self-delimiting condition?
Because we have it in the definition of prefix complexity. In prefix complexity, we want the program just written on the tape, and the program should stop without reading machine should stop without reading additional bits on the tape. So here we have some technical thing, I don't know why it's.
So this is actually not so important, probably.
Yeah.
No, it's not important whether it's prefix-free or plain complexity. But I used prefix-free complexity throughout all my PhD except at one place, so that's why I have these things. But also n is needed for other computations. But okay, if you consider plain complexity and so on. Now the definition of LTN is log STN.
Yeah.
So the number of programs that, if we have that information here in the lemma, then we obtain this inequality with ON constant.
So we have L of ti minus 1 here in the lemma.
Yeah. So that means that it is a task of I minus 1.
Yeah. So somehow we will look how the complexity of task Ti, if we know how many programs solve the previous tasks.
Yeah.
Okay. And can you explain why it's such a strange condition? What is the role of it? Why we are interested in this number?
Yeah, because I needed to prove it, otherwise, yeah.
Okay.
I cannot prove such a lemma without these numbers. These numbers allow to apply some coding theorem. So I can prove the lemma now.
Yeah, I'm very puzzled with the lemma.
What?
I'm puzzled with the lemma.
You don't understand the...
No, I understand the statement,
okay.
But it looks to me strange because we have n in the right hand side.
We have n here because it's implicit in the t, and we have n here because the large n, you mean?
The large n.
Yeah. So the large n is implicit in this t. Because
okay, proceed to the proof. Okay, I see. Okay.
So it's symbolic.
Okay.
Now I must remove something. I remove
this one.
Okay, you understood it already long before, so...
No, before you didn't say to us that L is actually the logarithm.
Oh yeah, now, except about the detail, yeah.
But you mean you want to know the logarithm, so you want to know this number
the integer part,
2.
The integer part of
the integer part, yes.
So you don't know this number, but you know it with the precision. You can have a lower and upper bound for it, which are twice, would differ by 2.
Yeah.
Which makes it even more strange.
Yeah. Because if you got the full precision, then the statement could be very trivial. Then, but that's a little bit deep into the mathematics. So I remove. now there are two cases in the lemma. The first one, case 1, is suppose that St n equals 0. That means there are no solutions. Then it's trivial, because then the complexity of the task must be larger than n, so we get this one. Agree?
No, but we can have solutions of shorter length.
Yeah, okay, but if you have solutions on shorter length, then you can put zeros after it until n, because you know n. So indeed, I should have taken an inequality in that definition.
Okay.
So that means that we can assume that there is at least one element in this set. Now we're going to use this set to define a semi-measure.
Excuse me, is it true that if the set is not empty, then the left-hand side is greater than the sum, not n?
So if the solution set is not empty,
you are going to prove that k of t is bigger than the sum.
yeah. So
And we can forget about n.
yeah. So we will take n sufficiently large in that case, so we can forget about it, and then we will prove that. So some more notation. So I will abbreviate L T. Can you see it? L T I. Estimating an intermediate inequality, which I will give, which I will write down.
So we need to prove that this k of t is large. The sum of this k of ti is small.
So we want to build an appropriate scheme vector.
And this is of course k after each given question e minus 1. So these are the same quantities, and we want to estimate this. And we can do this with the coding theorem applied on the semi-measure.
But can you explain me what is happening? Right? I don't know.
Yeah.
What is happening?
Okay.
Then
Wait a moment. I will check whether I don't have any mistakes, and then I will.
it doesn't matter. I don't understand what it is. So you can make whatever mistake you want without any damage.
Yeah.
So wait, I need time to read it. So we are interested in the for every particular z, we are interested in how many programs of length.
Yeah, of length.
So Ly is this number, logarithm of number of programs. Yeah.
So we do not specify the length of p, the program p, any length.
Well, P has to be in this set, which implies that it has
Length
to be length
L.
n. Yeah, large n.
So we consider the programs which solve the first I-1 tasks, and somehow we are interested in that it prints z, the program. How it may happen that so this solution then to the the first I-1 task.
Yeah.
And we consider Which particular solution we are saying?
So we can evaluate Pz, and it's
But wait, and Z itself shouldn't have the length L. It might have any length.
any length, yes.
So when we speak about solutions, we mean the length of solution. We mean the prefix code of the solution.
So I have some theory what is happening.
Okay.
Explain me. Please tell me whether.
Actually, I did not give an intent to explain this. I would just write it down. I was checking for errors, and then we started talking. So I will try once more to explain.
No, just don't do it.
Sorry.
Let me try to explain how I see what is happening. So we want to get an estimate for this sum on the right, the sum of this case. We need to prove that the sum is small. Mm-hmm. How do we do this? We look for a given n. We look on the program which solves our interactive tasks up to a certain point. This is the number of this program is Li, yeah. And the greater the Li is, the smaller is the greater I is, the smaller is the number of the programs. So this quantity Li minus 1 minus Li, this shows how much the number of program decreases if we require the program to make some additional step correctly. And if then we want to bound that the ith term of this quantity in this inequality, this ith term, this one, is bounded by this difference, I guess. And if this is bounded by this difference, then the sum is bounded by the difference, just the entire number of programs. So is this flat? Is this what you're trying to do, or you're trying to do something else?
Yeah. Now he told the remaining of the proof, almost everything of the remaining of the proof.
But how is the number of programs relates to the KFT?
Yeah. First, let's explain the left.
Yeah, but now you're going too far. I just have that definition. I wanted to explain only this step, and then you can.
I'm totally confused with the difference between Z and P. Before I understood that the solution is just the program which solves the task, right?
Yeah.
And now we have some intermediate Z.
Yeah,
what is the difference
Z
between?
is any candidate for a solution. So PZ defines the semi-measure. It's a parameter in the definition. So we make an enumerable semi-measure that depends on Z. So we can apply a coding theorem. And using that coding theorem, we will have a bound for the answer of Y. So we choose Z equal the answer of Y.
So it seems that we want to estimate the complexity in terms of logarithm a priori probability.
This P of AI is the probability that random chosen program from minus 1 correctly solves ith question.
Yeah. So you know that the program P solves the
No, correctly solves ith question, which produces Z.
Not Z, but if you can see the P of...
P is output distribution on the answers which produced by all the program taken randomly. I guess so.
Mm-hmm.
So I will explain in my words to be sure that everything is right. So we look among all solutions of programs that solve the first I-1 task. And Z is any candidate. So we look for all programs that also output Z. So Z may be a wrong answer or a good answer. We can enumerate them. And if we see that it produces Z, then we increase our semi-measure. So our semi-measure is growing in time. And this is a normalization constant to have it fine. Then given that semi-measure, we can apply the coding theorem to encode the right answer. Which gives...
What do you mean by encoding theory?
It's Kraft-Chaitin argument.
Yeah.
So if we have a machine which produces something with some probabilities, then we can transform it.
It is inequality between semi-measure and prefix complexity.
Prefix doesn't exceed the logarithm of semi-measure.
Yeah.
And here there is a conditional semi-measure and a conditional prefix complexity. So it's the same thing, but
after applying the coding theorem, we obtain this equation. Because LE is the amount of programs that solves the E task right, so the sequence until the E task right. So if we have E such programs, then here is 2 to the power LE. So we got 2 to the minus LE minus 1. This becomes 2 to the LE. So if we take the logarithm of it, then we obtain this equation. And this is of a lower bound for an upper bound for Kolmogorov complexity, which is written here.
One of the terms in the right-hand sum.
We're not yet here.
Okay. This is.
We just need to go from here to there. So if this is right, now here is everything that you need to compute that semi-measure PZ. So you understand from here to here?
I'm not sure I understand. So what?
Potentially,
Yeah.
it hasn't happened anything non-trivial up to yet, because
Where is non-trivial step?
no,
Yeah,
we need to understand how does it relate to the left-hand side.
Yeah, but I'm not yet there.
Okay.
So there is one more
Maybe
step.
you start from the end. How does everything here
Yeah.
relate to the left-hand side of your
Okay,
inequality?
I will make a little more. I will remove this. Then we need another intermediate statement.
No, start from the end.
Yeah.
At the end, you need somehow to relate it to the left-hand
Yeah,
side.
but it's the same intermediate statement. I hope nobody will be upset. Okay.
Сейчас, а у нас сложность отличается тем, что еще n большое есть от того, что у нас там, или сейчас. Как-то загадочно. Нет, наверное, у нас и там есть.
Yeah, it's enough space. So here we have an equality. So how do we obtain this? It's maybe better if we write. We obtain this like.
Сейчас. А такой вопрос. Верно ли, что на текущий момент мы примерно доказали все то же самое, только слева у нас вместо КТ LN примерно?
So the question is whether did we show something? Did we show this inequality of the lemma when k of t is replaced by ln on the left side, or not?
So
what we are doing now?
Нет. Мы доказали, там вместо ln нужно поставить n минус ln или что-то такое.
Сейчас мы доказываем, что на самом деле...
Но он доказывает не в ту сторону, как видно.
No.
I will.
Yeah. Colleague usually complains that I am interfering with the speakers and force them to do something else. So now you can. I won't interfere, but you should understand this and then explain it to us. We will sit quietly without relying on your.
Okay, proceed.
So we have this sum, which relates to this like that. And
why L0 is equal to L?
Because
all the
L0 is trivial task, and all programs of length n.
I see.
Now you have written the last equality. Why is it true?
Why is it true?
This is what is left to what we are left to prove exactly.
Yeah.
Because if we prove this, then we prove our lemma. Okay.
No, we should in other direction.
Yeah. So
but wait. Do not force him. We have proven this direction, right? Okay.
Yeah. I will now do every step here. So if you have a very short program, then you can put all kinds of string after it, and then you get many solutions of length n. So this shows that this inequality holds like kt is smaller than the number of solutions here.
It's greater.
It's greater. Okay.
No, wait.
The number of solutions.
So L is the total number of solutions, right? If we have a very small program,
Yeah.
then we can append anything to it,
Yeah.
and we will obtain n solutions. So if we have
So k of t is an upper bound for L minus n minus LL, yeah? Or what?
yeah.
Equals
Yeah.
equals k n minus kt. So if kt is very small, then we are close to. Oh, that's wrong.
Yeah, like that.
What I don't understand is the following. We want to prove that k of t is bigger than something. Why do we prove that k of t is it is bigger
No,
than
it is sorry.
So the idea is, if k of t is small,
Yeah.
then we have many solutions of length n,
Yeah.
right?
Yeah.
So how does it help to solve our intermediate tasks if we have many solutions? I
So
don't
if we
know.
have many solutions at the beginning, then if we make our task harder and harder, the number of solutions are easier and easier, relaxing. We don't ask for. So we will look for the program which solve all of them, and this program which solve all except the last one and the two last one and so on.
Yeah.
So if we have many solutions for the entire thing, then the increase is rather small. And this increase, as we see here, is an upper bound for the complexity. So the complexity is the corresponding terms in the complexity are small.
Okay, and if all the increases are small, then it means that the tasks are easy. We can encode them.
If some increase is small, then this complexity, the corresponding term in the sum is small. This is what is said.
Yes. Because we have that LT as condition, and given that condition, we can encode.
Just say it again. I would want to check this, to understand this again.
So
imagine we know LT
Yeah.
I minus 1 as a condition.
yeah.
Li minus 1 is a condition. So why this complexity of Ti is small?
And also we know the number of solutions. So how do we obtain the solutions themselves? That's not easy to understand. So,
which step are you looking?
Just why k of Ti is bounded.
Yeah, that inequality.
Okay. That inequality is by the coding argument. So I removed it, but I will write it again. We have that B A Y. Sorry, B A Y. Equals L E minus L E minus 1 minus L E. So how do we get that? We put in all solutions here. Then we will have about 2 to the power LE solutions.
But wait, how do we know if something is a solution or not? That's the problem. We don't.
But we have in the conditions all the previous things.
Okay.
Yeah.
How do we single out the solutions of the more complicated tasks?
That's the Shannon final code. He has to do that.
No, I don't understand.
We can enumerate the solutions of the previous, of a simpler task.
Okay,
And we say that if many of them can be used to solve the more complicated task, then the a priori probability of AI is small. So imagine there is not small difference between the number of solutions of more complicated tasks and less complicated tasks. That
isn't it true that this equality is by definition of P actually?
Yeah. Yeah, this is the
and
this is
A
the definition of
A
P.
super I minus 1 means all the solutions to the previous task, or what?
Yeah. Repeat.
What we are given in condition, QI.
Yeah.
What is QI?
all previous questions and answers.
All species, yeah.
And AUI.
AI are the answers here.
Do we obtain from this information all the solutions of the previous
Yeah.
task?
Yeah. So you can actually remove this. It's also fine.
I just get lost with this.
Oh no, you're right. It must be there.
Yeah.
It's
Q sub super I, what is it?
It's question 1, 2 until QI. So this Q until QI.
And A to the I minus 1. All the answers.
A1, all the answers
Except
except the one you have to solve.
So these are sets of answers actually. A1 is not one answer.
A1 is
No,
just
it's one
one
answer.
answer.
if you for one,
It's one answer, right?
Yeah.
Yeah.
And Q1 also is one question.
Yeah.
Yeah, it's one question. It's not.
Yeah. So you get lower is 1 and upper is a series. Super I, super I.
And given this information, we can enumerate all the solutions up to I.
Yeah.
And then we just single out from solutions of the previous tasks those who solve also the ith one.
Yeah. Exactly.
But wait, don't we need to know also AI to this, for this?
Yes, but we choose here an arbitrary set. And when the Shannon final code, we choose the right answer.
We choose just by its index. So the index indicates IC. We do not need IC. Okay.
So you can go from here to here?
I think I got everything. I got the proof.
And the last inequality, that n is bigger than big N minus k of t. That's why if k of t is small, then we can pad this program by anything we want, and
so we have many programs.
2 to the n minus k of t programs.
Yeah. This is exactly what we need here. So it's some kind of general statement, not related with our example. Just we want to, maybe we need to understand what is general meaning. So we have more and more complicated tasks, and we say that the entire so it's a kind of the dilemma said that additivity of information is true if we have additional conditions.
Yeah, if on the bound on the numbers, logarithmic number of solutions, then we can apply this.
So, but here we have as a condition not the complexities as in standard formula, but kind of a logarithm of the number of solutions.
Yeah. Of course, it will also work if you have the complexities, like you say, of the shortest programs, but then I cannot apply it further in the proof, so I need this version of the lemma.
So now we have some upper bounds for. So what is the role of this lemma? We want to get upper bounds for some online complexities.
Yeah.
And this is a way to get this upper bounds.
Yeah.
Lower bounds.
Exactly. Yeah. So
no, for online complexity. Oh yeah, lower bounds.
Yeah.
So what we needed are the lower bounds. Yeah.
Lower bounds. So we almost have lower bounds. We only have to deal with these L's. That's the role of the lemma. So the remaining of the proof is how to deal with these L's so that it does not harm the inequalities.
So we are going to get rid of them, actually.
We will show that their influence is small.
But why do we need at all Ly's in condition?
Because we want to apply the coding theorem.
Okay.
And then we have to normalize. If we do not normalize.
No, they are not computable. The sets are lower than computable. So we don't know when they all.
So
I see.
Some kind of.
Yeah.
So we have
lower bound.
So we have a lower bound for complexity in terms of standard prefix conditional prefix complexities of the each answer corresponding to all previous history.
Yeah.
And the which